So we continue with the discussion on numericals from modules 2 and 3. Today we'll take up say this question. So we wrote it yesterday, I mentioned it yesterday. So did you calculate it or did you get the answers? Did you calculate it? I think we had shown this. Hello? Can you people hear me? Hello?
Yes, sir.
So did you do the problem? Just calculate the volume flow rate and mass flow rate. The density is given, the diameter of the pipe is given. So from this you can calculate the area. Okay, D is the dia. So convert into SI units because this is in SI units. Okay, so convert into meters. Same. Flow velocity also you have to convert. And the value കിട്ടി? What value did you get? Someone type in the chat box the values. Units don't matter. So the volumetric flow is this value, 3.357 in 10 power minus 3 meter cube per second. People are just waking up, that's what. I'll pause the recording for a while. Okay, so you calculate these values. Okay, these two values. Say mass flow rate, just to the density multiplied by the volumetric flow. Okay, see if you are getting these values. If you don't get, just let me know. Next day we'll see. Unit conversions ഒക്കെ correct ചെയ്യണേ. So the next question is about the Orbis plate and Venturi tube. So if you recollect, the Orbis plate is just a small plate which is placed in the small plate with a hole which is placed in the path of this fluid flow, and the opening dimensions will be dimensions determine, or you say this small value d. So the parameters, the key parameter in Orbis plate is the coefficient of discharge, CD. So coefficient of discharge is 0.6. Usually for Orbis plates the coefficient of discharge is 0.6, and for Venturi tubes it's 0.99. One reason is that the Orbis plate is going to reduce the pressure head downstream. It's sort of blocking the flow. The pressure downstream will be reduced as much as 40%. Venturi tube, the pressure downstream, that is after the throat is the narrow part or vena contractor, whatever. So where the that is for venturi tube, it is the reduction pressure is around 10%. 10%. So due to the same reason, venturi tubes, even though they are complicated, they are going to be used in situations where you cannot tolerate reduction in pressures. And here in this problem, you have an office plate with and the venturi tube of the same dia. The throat size for the venturi tube is 75 millimeters, and the office plate, the diameter is 75 mm, and the differential pressure, that is before entering the plate and at the throat, that is P1 minus P2 is 250 pascals, and you are assuming the density of water as 1000 kilogram per meter cube. So there is a relation, even though we are going to use this differential pressures, say delta P, we gave a very simple expression, Q is equal to square root of delta P rho, delta P into K. അങ്ങനെ ഒരു റിലേഷൻ തന്നായിരുന്നു അല്ലേ. So this is the actual this is a much, and we also have an expression in terms of the cross-sectional areas. So here this is a much more what do you say, expression which is practically used in terms of the coefficient of discharge. You have the cross-sectional area also, this cross-sectional area pi d square by 4, coefficient of discharge, and then this is beta, d by d is beta. Beta എന്ന് പറയുന്ന ഒരു പാരാമീറ്റർ നമ്മൾ പഠിച്ചായിരുന്നു. I think we mentioned in the class, beta, diameter of the office placed hole to the dia of the pipe. Okay, so d by d, and there is a parameter which is called as h. H is the pressure head, P1 minus P2 by whole divided by rho, that is h, and the g is acceleration due to gravity, 9.8 meter per second square. So plug in all these values into this expression. So this is again relation which states that a square relation exists for the pressure. H is P1 minus P2 by rho. H is P1 minus P2 by rho. So this is the actual expression for volume flow of water. This applies for both orifice plate as well as for venturi tube. So you can use this expression. Only the parameter which is going to vary is the coefficient of discharge. So you can compute all the values other than CD for once, and then multiply with CD to get the volume flow rates for orifice plate and venturi tubes. Hope you are working. You're doing the problem. So this is the value for venturi tube. So you'll have to comment why these about these values. Okay. Why these are in this range? What is the significance? You may be asked to explain which one will be preferred for particular applications. So that is the way you analyze K2, K3 level questions എന്നൊക്കെ പറയുമ്പോൾ കുറച്ച് ഇതുപോലെയുള്ള സംഭവങ്ങളൊക്കെ വരും. That is knowledge level 3 എന്നുള്ള രീതിയിൽ വരുമ്പോൾ ഇതുപോലത്തെ സംഭവങ്ങളൊക്കെ വരും. So you will have to give your inference about the numerical answer which you have got. So be ready with the theory as well as the answer. So the next question is straight away about volumetric flow and fluid flow velocity. Here there is a pressure head and acceleration due to gravity 2 into gh, root of 2 into gh. There is a square relation. In this question you have incompressible fluid is say you assume it is water for the present, you will have to write. So say it has a pressure head of 2 kilogram per centimeter square. So there is a thumb rule. So 1 kilogram per centimeter square of pressure head corresponds to 10 meters of water head. So that means you have 2 kilogram per centimeter square. It is 20 meters of water head. 20 meters of water head. That means this much a column of length 20 meters of water. That is what. That is the pressure. So pressure exerted by a water column of 10 meters. This is for 20 meters. And from this you can calculate the velocity, fluid velocity as well as the volumetric flow. Area, all those things can be calculated. Okay. So this is straight away, you just plug in the values. You just copy down the formulas, work it out. We will just proceed to 2 more questions are there. Okay. So unit conversion in 3 ശ്രദ്ധിക്കണം. The critical ആണ്. ഇതിനകത്ത് വെലോസിറ്റിയുടെ യൂണിറ്റ്സ് തെറ്റാണ് കേട്ടോ. മീറ്റർ പെർ സെക്കൻഡ് സ്ക്വയർ എഴുതിയിരിക്കണം. മീറ്റർ പെർ സെക്കൻഡ് സ്ക്വയർ അല്ല അവരുടെ എഴുതിയാലുള്ള പ്രശ്നം. This problem straight away I just took a snap from a source. Okay, so I didn't notice it then. Then this is a simpler expression for fluid velocity. Whatever expression you are going to use, so you have to mention it. Say this is the fluid velocity expression for Orbis plate. This is a simpler expression. C coefficient of discharge into square root of 2gh. That is del h is P1 minus P2 by rho. So and the coefficient of discharge also you have the value. So earlier we had mentioned this as we had earlier mentioned a formula for the fluid velocity, the volume flow in this manner. So here it is root of 2gh. H is P1 minus P2 by rho. Here so just calculate the value. The final thing is about a Pitot tube. So Pitot tube, in fact this Pitot tube is mounted in a aircraft. So it's a fighter aircraft, and this, unlike commercial aircrafts, fighter aircrafts, they mount the Pitot tubes in the nose cone here in the forward part. Commercial aircrafts you will find it this portion. Pitot tube failure is going to give you wrong indication of the airspeed. Whatever you measure using a Pitot tube is called as an airspeed. It's called as airspeed. So here this Pitot tube is used to find the velocity of the fluid. Say the pressure difference. If you recollect the Pitot tube thing, it has, it's a tube like this, so it has when the air strikes this front part of the tube, it is going to be at standstill, and you are going to measure, that is, it is a stagnation. So you are going to measure the total pressure, PT, and so this inner part of the tube is connected to a pressure transducer. Say the outer part is called static pressure. So this is, you have a ring, static ring. So those tubes are connected to another pressure transducer, or still better, you could connect it to a differential pressure sensor. Differential pressure sensor measure ചെയ്താൽ മതിയല്ലോ, രണ്ട് ലൈനുകൾ തമ്മിലുള്ള. You can find out the differential pressures between two lines. Maybe a piezoelectric transducer is, this differential pressure sensor is put there. At one side you will get the PT, you will give the PT. The other side you will get say something like this. Say this is your pressure transducer. To one side you will get you will give this PT, apply the pressure PT, and on the other side you will apply the pressure that is a static pressure, and you are getting, so this is a piezoelectric crystal, say piezoelectric crystal based pressure transducer, and you are going to get an electrical output proportion. You are getting a voltage output, electrical output. So this is the pressure recorded by the differential pressure transducer. So it could be any of the differential pressure transducers. So the pressure delta P is 12.5 kilonewton per meter square. So it is in SI units. The density of air at that particular height is also given as 1.29 kilogram per meter cube. So you can, from this you can compute the airspeed. Okay, so airspeed can be computed, right? Calculate the airspeed. Airspeed calculated. Say Pitot tube is not used on aircrafts alone, it could be used in indoor applications also. For instance, you have a pipe or AC duct, say in HVACs, heating, ventilation, air conditioning application, you have ducts which carry what do we say, air, cooled air, warm air, all those things throughout the building. So if you want to measure the velocity, air velocity or the fluid velocity through this, you have portable Pitot tubes, something like this bend, and you could connect it. So this is the fluid flow through this pipe, and you could connect it to this could be connected to a portable pressure transducer, which will give out all those readings, and even it will calculate the velocity also, flow velocity. So such Pitot tubes are there. So as part of the assignment you will have to find out one Pitot tube data sheet. Velocity velocity 30. So 139 meter per second, 139 meter per second, right? So you will have to collect a data sheet for a particular search the net, find out the Pitot tube data sheet, I'll just show you how it is done. Okay, so that summarizes today's problems. The numericals for modules 2 and 3. Some typical questions have been done. Rest I'll give you as assignment. Two more questions are to be put. I couldn't put it yesterday because yesterday I was busy with your senior sessional marks. Okay, I'll just tell you how this data sheet is found out. Okay. I'll share a tab. Okay, so you can see whatever I am typing there. Can you see whatever I am typing there? Can you see whatever I am typing there? Pitot tube data sheet, right? Hello. Can you see? Yes. Can you see whatever I am typing on the screen? I had turned off the audio and I was speaking. Can you see whatever I am typing on the sheet? Okay. Yes.
Yes, sir.
Yes. So you will come across quite a lot of Pitot tubes. Don't go for the first one itself. If you just go to the first one, you will just find out something. We will see. Yeah, this seems. I just want you to have a look. Oh yeah. This is taking quite some time to load. That's what. Here I have a geo connection as of now. We'll just close one tab. Yeah, in fact it had downloaded something, right? It downloaded. Okay, I'll have to share another tab to show you the data sheet. This is the data sheet for a particular type of Pitot tube, say by a company which is called as Delta Fluid, and it speaks a lot of things. This is a particular Pitot tube. So the dias 10 millimeter to 5000 mm. This is not a conventional type. So two sets of holes also, the dual averaging. This is the construction. So you will just put this Pitot tube like this through the fluid flow. That means you can just screw it onto the head, and you are measuring the differential pressure. You are measuring the differential pressure, high pressure, low pressure. So this is the differential pressure that is measured, and so this is the total pressure is measured. Static and dynamic components. So differential pressure out ആയിട്ടാണ് കിട്ടുന്നത്. You will get a differential pressure out. So then types of fluid: gas, steam, liquid phase, diameters operating up to 600 bars. Then these are different models, mechanical things. One more data sheet we come across is I'll just show the data sheet. Okay, wait. So this is another data sheet. This is another data sheet. This is data sheet of another Pitot tube. So this is having a profile construction like this. This is your conventional Pitot tube which you have seen on that aircraft, everything. So this is bent like this. So different types of Pitot tubes also there. K type, L type. Then some Pitot tube with a thermocouple. Pitot tube L type with a thermocouple. So you can make a temperature measurement also. Temperature measurement can also be there, right? That is it. Also this is another one with straight type with thermocouple. So dimensions are also mentioned there. There is the total pressure pot and the static pressure out, both you are going to measure the so total pressure output and static pressure output. It's made up of composite material, inox. So this is one application which I mentioned. Say this guy is measuring the airflow velocity within a AC duct, HVAC duct, and readings can be obtained. So this is HVAC duct, and you can get the flow velocity values and even the temperature also. This has built-in thermocouple also. So that's it. So then there are other gadgets also, differential pressure transmitter sensor with display, all those things, ASL, all, and the velocity measurement, you have delta P, rho, all those things. The C, coefficient of flow of the device, and L type, this is the value. And you want to calculate the rho, you can calculate using this empirical relation. Just plug in those values, so you'll get the value for rho. So and airflow measurement also, they have given the typical thumb rules. Okay, typical thumb rule. So this is from Sorman Group. This is a particular company. Fine. So these are two data sheets of Pitot tubes. Okay, we'll stop here.